When we look at the number line on its own, we find it rather boring and monotonous. One number to the next. 1, 2, 3. However, what this line hides is that behind every number lies a story. Because the number line hasn't always been this way, it has undergone many dramatic changes as our understanding of mathematics has grown. If you attempted to explain the number line to people in ancient Greece, they would be bemused. So today, it is time we truly took a hard look at the number line and unearthed its many stories, dissecting it into its components and delving into their conception and evolution. This story will be one that spans the whole world, not just a few thinkers in ancient Greece, but cultures as far apart as China and India. And it will not just be purely about boring mathematical concepts, but also involve several facets of culture and history. The story of numbers is one that is untold, yet engrossing. And to begin, we have to trace the origins of the most basic element, the number. But first, we need a bit of backstory. Humans have been counting ever since they were around. Counting served many purposes, such as to measure the amount of food gathered, count livestock, keep track of time, and so on, but it was not standardized, so they could only think in terms of subjective quantity, using more or less. They didn't get round to saying actual numerals, like 1, 2, 3, in a written, standardized manner for a very long time. The oldest tally marks, the most basic and oldest form of numerals, were made around 40,000 BCE. They were likely for ritual practices or notation. Tallying could also serve more practical purposes, even before numbers. For example, if a farmer wanted to know if he was missing any sheep from yesterday, he didn't need to count 1, 2, 3, and so on. He simply needed to make tally marks the previous day and cross them off the next. And any leftover tallies would indicate missing sheep. Such is the simplicity of tally marks. The basic principle of leftover marks has persevered for a surprisingly long amount of time and has found its way into modern mathematics. Let's give an example. First, let's take the set of all natural numbers, or whole numbers, and call it set A. Next, look at the set of every single square number. This is set B. Now a basic question. Which set has more numbers in it? Common logic will dictate that the answer is set A. After all, numbers like 2, 5, and 39 are missing from set B, while set A has all of them, right? Wrong. To see why, simply draw a line from every number in A to every number in B. Is there any point where a number in set A can't link to one in B? No. These lines just continue going into infinity. Every number in set A matches every number in set B. In fact, every number n in set A aligns with the number n squared in set B. Both sets have an equal number of numbers. This concept, known as correspondence, was used by George Cantor in 1873 to make a groundbreaking discovery. One cannot count every single real number. This is often regarded as the birth of set theory and also indirectly led to this famous but flawed quote. Around the 3rd millennium BCE, the civilizations of Egypt and Sumer devised their own numeral systems that can be called the first known numbers, moving away from simple counting and cancelling and into actual numbers with which operations can be performed. This is likely due to the heavy influx of commerce in the bustling region, as different empires vied to attain certain resources to further their greatness. Thus, a method to quantify the amount of goods being traded, rather than using subjective terms, was needed. The Sumerians used cuneiform in their base 60 number system. That means there were 60 different digits in it, while the Egyptians used their hieroglyphs to symbolize numbers. Many centuries later, the Romans and Greeks each came up with a numeral system in the 5th and 3rd centuries BCE respectively, using their own alphabets to represent numbers. The Greek numeral was quite short-lived, lasting only until 50 CE, whereas Roman numerals only fell out of use 1,800 years after its conception in the 14th century. Subsequently, the Eastern Roman Empire fell to the Ottomans as Constantinople turned to Istanbul. Even then, its legacy can be seen in formal texts like essays and even clocks. You can even see them in this video. Eventually, the Hindu-Arabic numeral system was developed in India by around 700 CE and introduced to the West by Arabian mathematicians in the 9th century, giving us the numbers we have today. A millennium before the birth of Christ, fractions came into existence in Egypt. They were calculated using simple unit fractions. From there, further fractions, known as Egyptian fractions, could be derived. For example, a half plus a third is 5/6. 5/6 plus a quarter is 13/12. The number line had expanded from the natural numbers to the set of positive rational numbers. These numbers can be expressed as a ratio of two integers, and they were thought to be the final piece of the puzzle, the numbers that would fill the line. The fractions really seem to do the trick. Immediately after half comes 3/4, 5/8, 10/19. But counterintuitive as it may seem, there are numbers on the number line which are not rational. Numbers that defy common logic and the fanciful Western ideas of order and perfection in the universe. Let's find out who made such an unfortunate discovery. Let's take a simple isosceles right triangle with the length of the sides neighbouring the right angle being 1. Now let us assume we needed to find the length of its hypotenuse. It's the 5th century BCE. The Pythagorean theorem had already been discovered by, Pythagoras, and he has developed a cult of other intellectuals of the time surrounding him. These thinkers followed what one could call a set of moral guidelines that Pythagoras taught in his lifetime. One of his preachings was that every single number was rational. In fact, that was even their motto, all is number. Anyway, to solve the problem of finding out the diagonal, you use the well-proven Pythagorean theorem. The answer is the square root of 2. It obviously has to be more than 1 and less than 2, but what is it? Of course, it has to be the ratio of two integers, since every number is rational. But which two integers? You embark on this quest and get only approximations, inadequate approximations, and suddenly you come upon it. The realization that popular law has cost Greek mathematician Hippasus his life. There is no pair of two integers whose ratio gives you root 2. But why? Let's first assume that there is indeed a ratio that conveniently produces what we want, root 2. Let's make that a over b. Assume that this fraction is in its simplest form, so that they share no common factor. Now let's square both sides. A squared over b squared is 2. Now we can rearrange to isolate a squared. A squared is simply twice of b squared. Now what does this mean? Firstly, it means that a squared is an even number, right? It's clearly a multiple of 2. That means that a itself is even, because if a were odd, a squared would also be odd. Now the main problem. Since we know that a is divisible by 2, that means that a squared will be divisible by 4. Think about it. A would have a factor of 2 somewhere inside it, and when a is squared, the factor of 2 squares with it. So a squared is divisible by 4. This means that b squared, if you remember, is half of a squared, is divisible by 2 and is even. But if b squared is even, that means b is even by the same logic earlier. But that means a and b are both even, which means the fraction can be further simplified, going against our assumption that the fraction is in its simplest form. We have just proven by contradiction why the square root of 2 is irrational. Indeed, the discovery of irrational numbers, numbers that did not follow the rule of being rational, proved a true shock to the Pythagoreans, who are said to have thrown poor Hippasus into the ocean upon that discovery. But why? Another core tenet of Pythagorean philosophy is that numbers were divine and in some way connected to the gods. In fact, some who documented the organization of Pythagoreans saw the eponymous Pythagoras himself as being sent by the gods, and by extension his teachings, including the fact that all his number are divine. There simply could be no messiness or disarray in divine things, after all. And so, when the irrational numbers were discovered, it was contradictory to the Pythagorean and also the Greek way of life, which is why it was so hard to accept. Over time, the Greeks would come to embrace the ideas of irrationality and imperfection. After all, it was the Greek Archimedes who discovered the famously irrational constant pi. As compared to the rest of the numbers, which were discovered and then incorporated into mathematics relatively quickly, negative numbers have had a rather fragmented history. It was in the 3rd century BCE that we got the first reference to negative numbers in a book by Liu Hui, a mathematician during the Han Dynasty in China. But until then, negative numbers were mainly used as a deficit in the context of trade, so it could be seen through the lens of subtraction rather than a new discovery. For example, the wrought numeral system used by Chinese merchants was written in both black and red for a reason. Red was any positive cash flow or income, while black was anything that needed to be paid out or debt. It was mainly Brahmagupta, the famed Indian mathematician, who clearly laid out ways to deal with negative numbers. One of his works contains this long quote as to how to do so, which once again stems from the idea of profit and loss in trade. Concepts like negative and imaginary numbers have proven controversial in terms of their adoption. As an Eastern invention, intellectuals in places like India and China were very quick to adopt the concept, while those in Europe staunchly opposed it for 1,500 years. The Greeks did not really say much on negative numbers, essentially making it taboo. Its only noteworthy mention is where Diophantus wrote the equation 4 equals 4x plus 20, which when solved yields a negative solution. He simply called it absurd. To understand why, we need to look at the fundamentals of Greek mathematics, which is geometry, and in geometry you can't just have negative values, can you? Length, area, and volume are all scalar quantities, meaning they don't have any direction or polarity. Hence, they can't be negative, they only have a magnitude or a size. Even the messy irrational numbers could be signified with lines, root 2 with the hypotenuse of a triangle, and pi with the circumference over the diameter. Negative numbers did not have that place in geometry, which is why they were left virtually unmentioned by the Greeks. Negative numbers only really became standardized across the world with the discovery of calculus by Isaac Newton and Gottfried Wilhelm Leibniz. Sorry Leibniz, but Newton got there first. The number 0 was fully developed in India by the mathematician Brahmagupta, whom, if you'll no doubt remember, was the one who clearly laid out how to deal with negative numbers. In fact, if you see the same quote presented earlier, you'll see several mentions of 0. Until then, however, most mathematicians did not grasp the concept that nothing could be something. 0 was indeed used in civilizations like Mesopotamia or the Maya, but that was merely to serve as a placeholder, not as a number in its own right. For example, in the number 102, we see the number 0, but that 0 was merely used to indicate that we were not referring to 12. After its discovery in what is modern-day India, the Arabs, being excellent traders, brought the concept they learned and introduced it to the West. After that, there was widespread adoption of the number. Here's a simple question. What is the square root of -1? This was the question that the hero of Alexandria asked himself in the 1st century CE. And while it seems like a fairly simple question, it turns out that this has no real answer. Why? To find out, let's split the number line into 3 categories: the positive numbers, the negative numbers, and 0, and see if numbers from any of those categories can be the answer. Well, for starters, the square root of -1 obviously cannot be a positive number, for the square of a positive yields, well, a positive. The solution can't be negative either, because any negative number multiplied by itself produces a positive, because the negatives cancel out. Lastly, the solution can't be 0, because 0 squared is 0. Realize that we have effectively ruled out all the numbers on the number line, which means that no real numbers can be the answer. So what is it? The hero of Alexandria had no solution for this. It was the French mathematician René Descartes who, thinking the concept was absurd, decided to ascribe it a value I for imaginary. He used this to mock the idea of there even being a square root of -1, which is unsurprising for a person who thought that animals were mere automa or robots and can't have any feelings. Well, in fairness, he did discover the Cartesian coordinate system by watching a fly buzz around his room. Before that, the Italian Raphael Bombelli conceived a framework for multiplying imaginary numbers in 1572. Apart from that, however, imaginary numbers remained poorly understood until the 18th century CE. This is when cool mathematicians like Leonhard Euler and Carl Friedrich Gauss adopted and began to work with them. It was Euler who discovered the beautiful identity linking the two most famous irrational numbers, the imaginary number and the base of the number line 0. But as we've said before, these imaginary numbers can't go on the real number line. So what happened? The number line became a number plane, thus giving rise to the complex numbers. For example, 2 plus 5i is a complex number having both real and imaginary components. These complex numbers became points on this new two-dimensional plane. The x-axis signified real numbers, whereas the newly added y-axis represented the imaginaries. As their name says, these numbers can transcend the power of algebra itself. While irrational numbers stated earlier could not be expressed as the fraction of two integers p and q, these transcendental numbers can't be the root of a polynomial equation. What does that mean? Well, a polynomial is simply an expression involving any sum of integer powers of a certain variable. For example, these equations are all polynomials. The root or roots of a polynomial equation is simply its solution or solutions, the value of those unknown variables, and transcendental numbers can't be the root or solution of any polynomial that has rational coefficients. A coefficient is the fancy word for a number by which the variable in our polynomial is multiplied. So simply put, if a number cannot be the solution of any polynomial with rational coefficients, the number is transcendental. The existence of such numbers was put forward as a conjecture by Euler in the 1700s, but was only actually proven by Joseph Liouville, a French mathematician. He used this number, where every decimal place is a 0, except numbers in positions of factorial numbers. It was tedious, but he showed that it could not be written as the root of any polynomial with rational coefficients. After this realization, mathematicians suspected that pi and e were also transcendental. These were later proven with much difficulty. And there are loads of numbers which we don't know, that is to say, we haven't proven are transcendental yet. And that is the story of numbers. Advances in humanity's understanding of mathematics have brought the number line from simple notches on a stone to complex data analysis and rigorous proofs. The story of numbers is truly remarkable and represents how a group of completely unrelated people contributed to society in an invaluable manner. For without numbers, life on Earth would probably be unimaginable. This is our very first video, so a sub to the channel would be wonderful. Let us know in the comments how we could improve the video. Finally, thank you so much for watching.